Here we're talking about forces. A force is a push or a pull. These pushes and pulls are applied to something, and thus when we talk about a force, it must act on an object. In general, we're interested in the motion of the object, and we're looking at the forces that are exerted on it. So in these examples here, we have an athlete who is throwing a shot put. In this situation, we would say that the shot put is the object. The shot put has a push being applied to it by the athlete. In general, what we'll look at is the forces acting on the shot put and the resulting motion of the shot put based on these forces. Similarly, with the punching bag, the punching bag is an object that is feeling a force, is feeling a push on that punching bag due to the boxer sparring with it. And so, again, the punching bag has a force exerted on it. When a force is being applied or exerted upon an object, that force requires an agent, something that exerts that force. So, for example, if you throw a ball, your hand is the agent, and the ball is the object that's being thrown that is feeling that force. And if you are pushing or pulling, there's a magnitude associated with how hard you're pushing or how hard you're pulling, but there's also a direction involved, what direction you're pushing the object in, for example. And because of that, force is a vector. And being a vector, we need to give both a magnitude and a direction to a force. We can distinguish some types of forces based on the type of agent that they have. A contact force is a force that acts on an object by touching at a point of contact. So, for example, with a baseball and a baseball bat, there is a contact between the baseball and the baseball bat where the force is transferred from the bat to the ball, and thus the ball will feel a force exerted from touching the bat. On the other hand, we'll also see long-range forces, which can act without any physical contact. For example, a coffee cup will tend to fall down due to the long-range force of gravity. It doesn't have to actually be touching the earth to feel that gravity. It can fall even if it's in the middle of the air. And so in either case, we're looking at the types of agents for these particular forces. And although typically when we're looking at an object and looking at the forces acting on the object, we don't always particularly care what the specific agents are. We are just looking mathematically at the forces. It often makes it a lot easier to identify the forces that are being applied by looking at what agents are around the object and could be influencing the object in question. We said that forces are vectors, and thus when we're drawing a force, representing a force in a diagram, we have to represent it as a vector. So what we do, number one, is to model the object as a particle. For right now, we're not looking at any sort of detail of the motion of the size of the object itself, but we're looking at the forces being applied to that object, where the object is essentially treated as a point particle. The force is applied at the particle, and so the tail of the force vector is sitting on that object. We draw the rest of the force vector from the object so that the direction of the arrow tells us the direction that the force is being applied, and the length is proportional to the size or the amount of the force. Finally, we'll be dealing with many different types of forces, so you'll want to give an appropriate label to the force to show what the force is representing so that we can make sure that all forces are accounted for. We could have a force being applied to a box that's being pulled by a rope. In this situation, the rope is the agent. The rope and the person are pulling the box to the right. And so what we're doing is we are treating the box, although it has size, it has 3 dimensions of taking up space, we're going to treat that box as a single point. We're going to treat it as existing at its center of mass, and we're going to look at the force being applied to that box. And so if we want to show it as a force, we have the box and we have the force of the rope pulling on the box. Similarly, you could have a box being pushed to the right by a compressed spring. In the same idea, the spring is pushing the box away, and we're treating the box as a point particle, as a single point in space, and so we would show that force being applied as the box as at a single point, and the force pushing it to the right, and so we have the arrow headed to the right as well to show us the direction and magnitude of that force. Finally, we could have gravity pulling downward on a box, and so the gravity is acting downwards. We're still treating the box as a point particle, and so we would show the force of gravity acting downwards on the box as a point particle. Here, the Earth would be the agent of the force, because the Earth is the thing creating the gravitational force that pulls objects towards it. And we'll see more detail on that later in this module. We've seen several different types of forces that can be applied to an object, and typically in typical situations there are more than one force acting in a given situation. When we're looking at several forces being exerted on an object, we're interested then in the net force on the object, which is the vector sum of all the forces. That's what we see here. The net force is, here is summation, here it is as a summation. It's saying the summation, the adding up of all the individual forces. And what we see in practice is looking at all of these different forces acting on a given object, treating them each as vectors, and doing a vector addition of all of those forces. This is what's called a superposition of forces, and that's something that we're allowed to do quite a bit in physics, where we're looking at the influence on an object of many different forces. We can look at the influence of each different force separately, combine all of their influences, combine all of the forces as vectors, and find one net vector that includes all of the contributions of all of those different forces. One example of that is if you have a box that's being pulled by two ropes. You have the box that has one rope pulling one way and another rope pulling the other way. We treat the box as a point particle, and when we draw them as vectors, we see the box has one force pulling it downwards, and that box has another force pulling upwards. Since there are two different force vectors acting, we have to find the true vector is the vector sum of the two different forces. And by using the tip-to-tail method or using the parallelogram method, we see that the net force will actually be somewhere in between those two vectors.